Ever wonder what really makes your phone or computer feel so ridiculously fast? Well, it's not just about the processor speed. There's this invisible hero working away behind the scenes called the cache. And in this explainer, we're going to crack it wide open and see just how this amazing piece of engineering solves one of the biggest problems in all of computing.
Okay, so here's the fundamental problem every single computer designer runs into. On one side, you've got the processor core, just absolutely hungry for data, operating at these insane speeds. We're talking nanoseconds. But then on the other side, you've got your main memory, the RAM. Now it's big, sure, but it is brutally slow by comparison. And that massive gap in performance, it creates this huge traffic jam, a bottleneck that would bring any modern processor grinding to a halt.
So what's the brilliant solution to that traffic jam? It's cache memory. I want you to think of it like an exclusive, high-speed VIP lounge right next to the processor. So instead of the CPU having to make that long, slow trip all the way out to main memory every single time it needs a piece of data, it just checks this tiny, super-fast cache first. And if the data's there, boom, performance just skyrockets. This is the core idea we're going to unpack.
Right, so how does this little magic black box actually work? We're about to pop the hood and take a look at the actual blueprint of a cache. How it's designed, how it's organized, and the core philosophies that guide how it's all put together.
Right off the bat, designers have a big choice to make. Do they go with a unified cache, which is basically one single pool of memory that holds both the program's instructions and the data it's working on? Or do they create a split cache, with one specialized cache just for instructions and a totally separate one just for data? See, the unified one is simpler for sure, but a split cache can seriously boost performance by stopping instructions and data from fighting over the same real estate.
But no matter which kind you pick, all caches are built from the same basic building block, the cache line, and each line has three key parts. First, there's the data section, which, you guessed it, holds the actual chunk of info copied from main memory. Second, you've got the directory, or what we call the cache tag. This is absolutely crucial. It's like a little label that says, hey, this data right here came from this specific address way out in main memory. And finally, you have status bits, little flags like a valid bit to say if the line is actually in use, or a dirty bit to track if the data's been changed.
And now for the main event, the lookup. This is what the cache is doing millions, if not billions, of times a second. It's this high-speed, precision operation for figuring out if the data the processor is screaming for is already sitting in the cache. Let's walk through it step by step.
So it all kicks off when the processor requests data from a very specific memory address. That full address gets sent over to the cache controller, which acts kind of like a hyper-efficient librarian. And the controller doesn't just see one long number, it instantly breaks that address down into three distinct fields, and each one has a very specific job to do.
The first piece of that address is the set index. You can think of this part like a row number in a spreadsheet. The controller uses these bits to instantly jump to one specific row, or set, in the cache. It doesn't waste time searching the entire thing, it knows exactly which row the data has to be in, if it's there at all. But here's the thing, just finding the right row isn't enough to guarantee it's the right data. You have to remember, lots of different main memory addresses can all map to that same row. So for the final check, the controller takes the tag portion of the address and compares it against the cache tag that's already stored in that line. This right here is the moment of truth.
And if those tags match and the valid bit is turned on, then congratulations, we have a cache hit. This is the absolute best case scenario. It means the data is valid, it's the exact data the processor was looking for, and it gets sent to the core at maximum speed. That whole slow, painful trip to main memory, completely avoided.
But if the tags don't match, or if that line isn't marked as valid, well, that's a cache miss. The data isn't there. And now the controller has no choice. It has to pause everything, go all the way out to that slow main memory, grab the entire block of data, and load it into the cache. This process is called a cache line fill, and it's the performance penalty we are always trying to avoid.
Now, the simplest way to build a cache is something called direct mapped. On the surface, it's really elegant and super easy to implement. But as we're about to find out, that simplicity hides a pretty critical performance flaw.
So here's the deal with a direct mapped cache. Any given address from main memory can only go into one specific line in the cache, period. There are no other options. What this means is that thousands, maybe even millions, of different memory locations are all fighting for the exact same spot. And you can probably see where this is going.
Let's play this out in a real disaster scenario. Imagine your program is run in a loop, and it needs a piece of code we'll just call routine A. The first time through, the cache controller fetches routine A and puts it right in its designated line in the cache. Okay, so far so good.
But right after that, the program needs to call routine B. And just by a terrible stroke of bad luck, routine B maps to the exact same cache line as routine A. So to load routine B, the controller has to kick out, or evict, routine A. Then, of course, the loop comes back around, and now it needs routine A again, which means it has to evict routine B, and this cycle just repeats over and over and over again.
This absolutely performance-killing cycle has a name. It's called thrashing. It is a software battle for the exact same location in cache memory. The cache is just constantly kicking things out and reloading them, causing miss after miss after miss. It's a perfect example of how the cache, a thing designed to make everything faster, can actually end up slowing things down a lot.
So how do engineers get around this thrashing nightmare? Well, they came up with a really elegant and much more flexible design called set associativity, and it cleverly builds on the concepts we've already looked at.
Okay, so instead of just having one lonely slot per row, a set associative cache divides the memory into multiple columns, and we call these ways. So now, when the set index points to a row, it's not pointing to a single cache line anymore. It's pointing to a whole set of lines, one in each way. Honestly, the difference is night and day. With that old direct mapped cache, a piece of data had one and only one place it could possibly go. But now, in a four-way set associative cache, that same piece of data has 4 possible spots it can land in within that set. And more options means way less chance of a conflict. Let's replay our little disaster scenario with this new design. The program calls routine A. The set index points to the right set, and the controller just places routine A in the first open slot it finds, way 0. Simple, no problem at all.
And now, the program calls routine B, which maps to the very same set. But this time, it is not a disaster. The controller sees that way 0 is already taken, so it simply puts routine B into the next available spot, way 1. Both routines can now live happily ever after in the cache, at the same time. There's no conflict, there's no thrashing. And just like that, with a little bit of clever architectural thinking, the problem is completely solved. By adding this flexibility, by adding these multiple ways, we've dramatically cut down the chances of those performance-killing conflicts and made the cache a whole lot more efficient.
So what's the big takeaway from all this? Well, it's that cache design is really a game of trade-offs. It is the critical bridge that spans that huge speed gap between the CPU and your RAM. The simple, direct-mapped design is cheap, yeah? But it's fragile, and it's easily broken by thrashing. The more complex, set associative design costs more in terms of hardware, but it pays for itself 1,000 times over in real-world performance.
And that brings us to one last thought. The next time an app on your phone feels incredibly snappy or a program on your laptop loads in an instant, just remember this invisible dance that's going on. These deep architectural decisions, these trade-offs between simplicity and complexity, are happening millions of times a second just to give you that seamless experience. So, how does knowing this change the way you think about the technology you hold in your hands every single day?